Hi everyone, my name is Omar Silva. I'm the co-founder of RoboGeek Canada, and today I want to show how to visualize the Dijkstra algorithm using Python Turtle. Okay, I'm going to use a code that I found very interesting from Geeks for Geeks. I'll put a link into the website. And it talks about the Dijkstra Shortest Path algorithm. It goes in a fairly good detail on how the algorithm works. And there is also written in different languages, C++, Java, Python, or C#. We're going to use Python. And if you scroll all the way down, you'll see that there is also the video that I also put the link where you can watch the explanation of how the Dijkstra Shortest Path algorithm works. Okay, so the purpose of today is not to actually go through this code. This was actually developed by DaVinci and Meta. But I'd rather take this code, and what I like to do is use Python Turtle to visualize it. Okay, so what we're going to do is copy this code. Okay, we're going to start a new Python file. Okay, so a new Python file. We're going to save it as, let me put my documents, courses, free tutorials. And we're going to call it Dijkstra. Let's call it module. We'll call it Dijkstra example. Okay. And we're going to paste as it is. Okay. Let's make sure everything's in. If we run this code as it is, there will be a couple errors that are easy to fix. I believe it's because this was developed using Python 2 versus Python 3. So first error, Python 3 requires that you use parentheses or brackets when you're using the print statements. So we can fix that fairly quickly. Okay, I don't think there's more thoughts. Okay, we'll run one more time. Okay, this is also an error because of the splitting the line. We can fix that by just doing like this. So we'll run it again. Okay, and then the last error is that it doesn't recognize this max integer. So in Python 3, we have to replace this with max size. So let's do that. So replace this guy here. So one way to do it is look for it. So what is max int integer? So we look for that. No, so this is one. Okay, so let's replace that with max size. And this one as well. Okay, let's run it. Okay, and you can see that we get the same answer as in the example. Okay, so in vertex 0, the distance from the source is 0. For vectors 1, the distance from the source is 4, and so on, where 8 is 14. So we get the same thing. So going very briefly, like I said, it's not the purpose to explain this code, but basically we take this map or graph that is a 9 by 9 graph of 9 columns, 9 rows that basically says the distance between vertices. So for example, this being vertex 0, vertex 1, vertex 2, all the way to vertex 8. So the distance between vertex 0 to vertex 0 is 0. The distance between vertex 0 to vertex 1 is 4. So therefore, the distance between vertex 1 and vertex 0 is 4. And you can see that the same happens in vertex 7, which is 8. And then you will see in vertex 7, with respect to vertex 0, is 8. So we have a graph. And in this graph, what we're looking at is determining what is the shortest distance from the vertex 0 to any of the vertices. No? So for example, if you go to vertex 5, it will take, the distance is 11 from source. From vertex 4 is 21, and so on. The code is good, but it's hard to visualize how you get to that answer. It's hard to verify that that's the answer unless you draw it or try to figure it out yourself. It's not such a big graph, so it's doable. But if the graph was a little bigger, let's say 25 by 25, it would be very difficult to verify if we're getting the right answers. So one way to do this is by visualizing. So what we're going to do is use Python Turtle to visualize. So we're going to close this example. And what I did is take the same code that we fixed and call it, we're going to save it as, let's put it in the same tutorials. We're going to call it Dijkstra module. Okay, so we're going to take the same code and make one slight modification and remove the main portion. Okay, we're going to detach the class from the main. So we're going to call this the module that we're going to access. One modification is that we're going to create a path list. Okay, that's empty. So this is an additional to track the sequence of vertices in the path. So for example, if I'm going from vertex 0 to vertex 8, I want to know what vertices I visit in the process. So as we are doing this, finding out which is the shortest distance or finding out the path to get to the node or to the vertex, we're going to append the information. No, so in this case, we're going to be appending uv, self-graph u of v, and the distance v. So basically, all the information available from the algorithm. I highly encourage that if you want to understand how this works, is try to do some print statements to see at every step what is happening. And again, go through the website and the video. They do a great job of explaining this. Okay, so having this path, we also know now the steps or the sequence of vertices visited. So we're going to have this Dijkstra model. Okay, now let's start a new file. Okay, and put this in. And we're going to save this guy and same thing. So this guy, we're going to call it Dijkstra understand. Okay, so we're going to create a couple functions to understand how the algorithm works without visualizing yet. No, so visualizing will be the second part. But first, let's understand, having the module, how can we access the information? Okay, so we're going to call this guy part one. Okay, so we're going to import everything from the module that we just created. Okay, and now we're going to do the same test because we know the answers. No? So we're going to create a graph of 9 vertices, populate the graph, and then we're using the Dijkstra, and this is the vertex 0, and the output will be the path. Okay, so let's run this. Let me see if I have spelling. Okay, so we get the same answer. If you notice, in the code of the module, there is a print solutions that is called as soon as you call this function or method. So it will give you the answer, which is good. Now, since we created these paths, let's print what is in there. Now, so we're going to make a space in between and then print. Okay, so you can see that in this case, what we're printing is that from vertex 0 to vertex 1, the distance is 4 for a total distance of 4. And you can see, for example, from vertex 0 to 7, the distance 8 for a total distance 8, or the shortest path. From vertex 1 to 2, the distance between these two nodes is 8, but the total path is 12 because you have to add the 4 going from 0 to 1. Okay, and so on. So this one gives us all the sequence or the paths that from node to node and the distance in between and the total path. Okay, the other thing is if you notice, so in the first one, 0 to 0 or vertex 0 to vertex 0 is always going to be 0. So 0 to 1 is 4. 0 to 2 is 12, which is here. And in this case, it's easy because the only way to go is 0 to 1, 1 to 2. But if you do something like the vertex 3, it's not so simple because you can get to that in from vertex 5, which it takes 25, or you can go from vertex 2, which is 19. But because we're interested in the shortest path, we're going to select 19. I'm going to pick another example. Let's say vertex 8. No, so vertex 8, you need to come from vertex 7. So 8, and then coming from vertex 7 will give you a total of 14. Okay, or alternatively, if you go to from vertex 2, it will be longer, no? Because you have to add the 14 plus the path from 2, etc. Okay, so this is the information we get from paths, okay, which is very useful. So we're going to create a function now that we're going to call it understand graph. Okay. So we're going to modify this same thing. We're going to print all the path, but this time I'm going to do this sequentially, just to be more organized. So let me put this code here. Okay, so print all the possible paths. We're going to take the vertex source, the vertex destination, and the distance between the vertices. Not the total distance, only the distance between them. Okay, so if we run, this won't work unless I code it. So if we run this, now you can see that from vertex 0 to 1, the distance is 4. From 0 to 7 is 8. 1 to 2 is 8. 7 to 6 is 1, and so on. The other thing is important. You can see that even though there is 8 vertices or 9 vertices, there is how many paths? 2, 4, 6, 8, 10 paths. Okay, so there are vertices that have multiple paths to get there. Okay, so now that we know all the paths, let's try something else. So let's sort them from the vertex destination. Okay, so from the second vertex. So let's say if we go from vertex 0 to 1, then vertex 1 to 2, I want to organize it in that sequence. Okay. Let's do that. So we sort the paths in order of, should say, vertices. And we use a sort function with the key lambda that takes the second or index 1. So remember, in the index you start with always with 0 from the list. Okay, and then similar thing, we're going to print. I put this /n to make a print spacing. So let's run it. And you can see now that it's a path that is sorted. So 0 to 1. So you can see it's 1, 2, 3, 3, 4, 5, 6, 7, 8, 8. Now, so it's easier to see that there's 2 paths for 8 and 2 paths for 3. Okay, everyone else only have one way to go. Okay, one path to go. Okay, so let's do a little more digging. We're going to create now a function that tells me if there is 2 ways to go to a vertex. I'm interested in the shortest way only. Okay, so we're going to create a function called shortest path. Let's put it here. That's going to take the path, what vertex you're visiting or the destination. So it's going to find out the possible path and only interest in the one that has the shortest distance in between. Okay, so the vertices, so that's, or the path line, sorry. So this will be the index 0, index 1, index 2, index 3. So I'm only interested in the total path length, and I'm interested in the minimum amount. So this function finds that. So let's use it. Okay, so we're going to find the shortest path from V0 to V1 and then V0 to V2 and so on until V8. Okay, so let's run this. And you can see that now the shortest path from 0 to 1 is 4, from 1 to 2, the distance between the two is 8, but the shortest path is 12. And now you can see for the vertex 3, the shortest path is 19, and so on. And that should match this number originally found here. Okay, so what this is helping us is that now, with this information, we can also find out what are the visited paths, visited vertices. Okay, so how do we do that? Okay, we're going to have another function that we're going to find the visited vertices. Okay, so let's put it here. So this function is going to take the path, the destination vertex, and we're going to start with the destination and go backwards. Okay, so until we find the source node, which is the 0 vertex, and we use the shortest path to figure out we're only interested in the shortest path and appending this path. So for example, if I'm going from vertex 8, I find out what is the shortest path, add this, then find again the shortest path until I get to 0. And I'm going to return these visited vertices. Okay, so let's use it. So okay, so the sequence to reach the vertex destination. So again, we're going to do it from 0. So we're interested in to find from vertex 1 to from vertex 0 to vertex 1, 2, 3, 4, 5 till vertex 8. Okay, so that's why we start the range at 1. Let's do this. Okay, so now, so if you want to visit to go to vertex 1 from 0, it's only one way. No? So you go from 1 to 0. If you want to go to vertex 2, you have to go to vertex 1. You come from vertex 1 and then go to vertex 0. So we're going backwards. To go from vertex 3, you go 3 to 1, 0. From vertex 4, you go 5, 6, 7, and then 0. And then from vertex 5, you go 5, 6, 7. From 6, 6, 7, 7, 0. And then from 8, you go to 2, and 1, and 0. Okay, so if you see the distance between 8 and 2, just to take this example, is 2. So that will be, and then from 2 to 1, we know it's 8. So 2 plus 8 is 10. And then 1 to 0, we know is 4. So 10 plus 4 is 14. That's the total distance traveled. So now we know the sequence that we need to visit the nodes. And that's going to be good for the animation purpose. Okay, so we're done with this piece. I'm going to now start a new file. Let me save this one. Okay. And let me bring it up. And we're going to do the visualization piece. Okay, so let's save this guy as visualize. Okay, Dijkstra visualize. Okay, so this will be our part 2. We're going to import stuff and including the graphic library. So turtle, random and time, and the other two modules that we created. So this one can go now. Okay, very simple. We can create a turtle object as this. To make the graphs a little faster, we're going to select speed 2. We're going to hide the turtle, and we're going to create vertices of radius 25. So for this is the tricky part. So how we visualize this? So let's say you have vertex here, here, here. I'm going to call this guy vertex 0, and this guy vertex 1, vertex 2. Okay. So when we're visualizing this, we not necessarily know the distance between them. Okay. And they may or may not be connected. So for example, we know, for example, the vertex 0 to vertex 1 has a distance of 4, but the distance between vertex 0 and vertex 2 is 0. No, but we know that the distance between vertex 1 and vertex 2 is 8. Okay, and the graph may change. No, so it's actually 9 vertices. So to represent it can be very dynamic, and if this distance changes, we need to have a flexible way to represent the graphs, the vertices, the distance in between them. So how do we do that? So let me put this down. So first we need to generate vertices. No, so we're going to create a function. We're going to call it visualize graph, and we're going to do it step by step. So let's call it here visualize graph. Okay, so we're going to start by first generating some vertex locations. Okay, so let's do this. We start very slow. We're going to generate randomly locations in the screen. Okay, so from minus 300 to 300, so basically the length of the screen, separated 100, and that gives me X and Y. So we can test these by saying, for example, print generate vertex location. Okay, let's see what happens. Okay, so it will give me, minus 300 and 300, and it open also the Python turtle. Okay, we're going to, it's going to get annoying if we keep printing this, so let's make a slight modification to the other file. Let's do that. One second, guys. Yeah, so we're going to just feel a little lazy. So we're going to replace this guy by this. No, so when we call the module, it won't print it. It only will call it if we call it within the module. Okay, so test it again. Okay, we get this and that. Okay. Now, so now that we did, we generated a single coordinate, we can do this to generate more coordinates. No, so we need 9. So we're going to create a function that says generate vertex locations. Okay, we're going to put an input of 9. Because our graph has to be 9 by 9, that's from the example, I put a condition. And then it will keep going until it creates all the vertices. And it's looking that the vertices don't overlap. No, so this is what it's looking. If the vertices overlap when you generate it, we'll skip it and create another vertex. And it'll keep going until it has 9. Okay, so so we're going to replace this one by this. Okay, and if we want to understand what is this happening, we can just do print vertices. Okay, and this gives me the 9 vertices location coordinates xy. Okay, so now that I have the locations, we need to start doing some drawing. So let's do that. So we need 2 functions that we're going to use. So the first function is draw vertex that takes a coordinate of xy, radius of the vertex, and the counter, because as we draw the vertices in the screen, as such, we need to also put a label. No? So we're going to label them B0, B1, B2, and so on. So program is simple. We're going to pen up so we don't make a big scratch in the screen. Go to that location, draw a circle with the radius that we determine, and then we're going to write the text with V and the counter, which is the number that of the vertex, and print the message. Okay, so that's for a single vertex. For the draw vertices, which is all of them, we basically take the vertices that we generated and go over all of them. Okay, so how we call it, very simple. We're going to now draw vertices, take this vertices list, and radius that we define as 25. Okay, so if we run this, it'll be in random locations all the time because we decided to use random. So for example, V0 is in here, upper left corner, V1 is all the way down, V2 is somewhere here. But if I run this program again, because it was randomly generated, V0 will be in another location. So V0, V1, and so on. If you want to adjust this, you can play with the weight that the vertices are generated. Okay, so this is not perfect, but it helps to understand the code. Okay, so now that we have that, we want to find a way that we draw the distance, so this number distance in between, so in between the vertices, but we're going to use a dashed line. Okay, so the dashed line makes it easier to visualize. Okay, so let's continue. So the paths, we're going to be drawing it using dashed lines, okay? And then we also need the number or the distance in between the nodes. So for this one, we're going to create first, and I'm going to explain it quickly. We're going to draw a broken line. Okay, so a broken line is basically, we'll take the coordinate of the first vertices, the coordinate of second vertex, and the distance between them. Calculate, so it'll go first to the location of the first vertices, calculate the direction and distance going into the second vertices, set the heading, so basically rotate to that direction, and then instead of going forward all the way in that distance, we're going to do it in steps. So to create the broken line, so that means we're going to forward 10 with pen up and then pen down and forward 10 again. And finally, we're going to add the label, but we're only going to do it at 20% of the distance between the vertices, or if use 60, because if the distance is too small in between the vertices, the label won't look good. If it's too far, it doesn't look good either. So 60 is a good number. So it will select either the minimum or the 60, but it won't go too far. And you can play again with this. And we're going to use blue color for drawing, writing the text. Okay, it's a distance. So that's what broken line does. We're going to also create a function called draw path line. So it will take the vertex 1, vertex 2, the radius, and the distance between the vertices. And it will determine where the vertex on top, to the below, to the right, or to the left. Okay, so why is that? So if you have two vertices, let's say in this case we have two vertices, no? So we're going to play different scenarios, like where vertex 0 is a vertex 1, and let's say you want to connect them. So ideally, you want to connect from the bottom of this circle to the top of this circle. If the vertex 0 is below vertex 1, then you want to connect this way. Okay, so it depends on the direction. Same thing, if the vertex is to the left, you want to connect from the left side of the circle. If it's to the right, you want to connect from the right to the left side of the second circle. So this is what this code is doing, is deciding from what end of the circle we're going to draw. That's why it has the radius. And finally, which is where we're going to spend a little more time, is drawing all the path lines. Okay, so we're going to use the color red. We're going to go through all the columns and the rows of this graph. Now, so the graph that let me open it here. This graph. Now, so we're going to use this graph and go through all the rows and columns. But in this case, if it's the distance between the vertices is 0, we don't care. we don't want to draw these lines. We only want to draw if there is a distance in between them. So that's one of the conditions here that you can see if it's 0. You don't want to draw between the same current vertex and the vertex that you're visiting. Okay, and also if the row is greater than the column, it means that it's already been visited. So no need to do it twice. And we draw the path line, okay, where it takes the current vertex that you're visiting to the vertex that you are going, so destination vertex, radius being standard, and the distance between the vertices that we read from the graph. Okay, so if anything, this is where most of the logic of how we connect the paths, this is the important function. This one is more aesthetics. It's where we're connecting the lines. And this one is a simple connection of lines, just making it broken. Okay, so now that we have these functions, let's draw it. So let's do this. Okay, so let's run this. What we get? So we get random locations, and now we're drawing the distance between the vertices and all the connections that are valid. Okay, we're not connecting. So for example, V0 to V2 is not connected because the distance between them is 0. And you can see now the representation. So the number that is closer to the node is the distance, is the source node. Again, this is where the 60 comes from. It's okay for the majority. In some cases, it doesn't look that great. Now, for example, when the nodes are in the same level, it's a little confusing, but okay, that's room for improvement. So now that we have all the paths, we want to show the sequence of how we determine the distance, the shortest path. No? So for that, we don't need to create more functions. What we're going to do is use the functions that we created in the prior Python file, that's the Dijkstra understand. So we're going to put a small time delay just to see the animation. And we're going to find the vertices that we want to visit. Okay, and let's print them. In this case, I want to go from V0 to V4. Okay, so let's run this. Okay, so it's visiting all the okay, and it's telling me that to go to visit to vertex 4, it will come from vertex 5, vertex 6, vertex 7, and vertex 0. So last thing we need to do is animate that. So how we do that? Very simple. We're going to do a small loop with color orange. So all the vertices that are visited, we're going to paint them in orange. We're going to use the function draw vertex. In this case, it's the vertex, x coordinate, y coordinate, same radius. And in terms of the number, remember this is the number, we're going to use the vx. Okay, and we're going to put a little delay in between. Okay, and that's it. We now show that the vertices that we animated was 4, 5, 6, 7, and then 0. Okay, so if you miss it, we can increase this to 1.5 seconds just to make it a little more visual. Okay, so we create the vertices, we connect the vertices path with the distance. Okay. And then finally, we're animating from vertex 4 to vertex 5 to vertex 6, vertex 7 to vertex 0. And that's it. Full visualization using Python Turtle. Thank you. I hope you enjoy.